In this discussion, I will talk about how the backing loss in CMUTs, which has been produced by anodic wafer bonding technology, uh, have or include vibrational dampings in their backings, and those appear to be baselines in the impedance measurements you take from impedance analyzers. So the baseline that you have in the measured impedance data are very much suggestive of the losses in the substrates in the form of pressure or shear waves present in the backing solids. Okay, so the CMUTs they can be thought of as like bilateral CMUTs, which are not only coupling energy into the front medium, but they are also coupling energy into the backing in the form of pressure and shear waves. Okay, so the measured data is very much suggestive of such vibrational losses in CMUT. So in this presentation, I'll talk about how these losses can be characterized and those substrate impedances, how they can be included into the circuit models of CMUTs, and that should give the proper noise figure of the CMUT as a consequence of the circuit model. Okay, so let's I'll briefly talk about acoustic impedance before showing you the impedance data. I'll talk about the impedance of spherical waves in solids. So there's not much that has been said previously about the acoustic impedance of such spherical waves which are propagating in isotropic solids. There is some work which has been reported and derived by Blake in Journal of Acoustical Society of America. And what he reports is that if you have a spherical radiator point source, spherical point source, which is radiating spherically into the solid, let's say substrate or a rigid substrate, then its impedance can be represented in it has both real and imaginary parts, as you have in fluid mediums or let's say soft polymers like RTV rubber as a function of frequency. Now here, rho and C are usually they're the density and speed of sound in the medium. So these are this is the acoustic impedance of the backing material. So subscript B is showing you that this is the speed and the density of the material of the backing, and S is the area of the radiator. Okay, so the normalized radiation resistance, the real part, is very similar to what we have in fluids, which has Poisson ratios of like 0.5. Water has a Poisson ratio of 0.5, and these materials, they don't support shear wave propagation. Mostly it's the longitudinal or the pressure waves that are present in the fluids or air. So it's very similar. The radiation resistance has a very similar dependence on frequency. K is the wave number in the medium, A is the aperture size of the radiator. So it's very similar to what you have in, for example, in fluids. So the story is very similar to what you have in solids. But on the other hand, the radiation reactance, that is the imaginary part of the backing impedance, is quite different. It has a dependence on the Poisson ratio. So you can see the factor K that is coming into the expression, as Blake has reported. This factor K, if you expand this radiation reactance term, and it can be bifurcated into these two terms, you can see that the second term, if it is a fluid, let's say sigma is 0.5, then for like water, you don't have the second term, right? I mean, K vanishes, which means the shear waves is not supported in fluids. So the reactance is very similar to what we have in fluid mediums like oil or water. So, but in solids, the story is different. So the reactance is dependent on the Poisson ratio of the material. And it turns out that for materials which has, let's say, Poisson ratio less than 1/3. So for example, if you look at this red curve and the blue curve, the reactance is compliant. That is, it is sort of a capacitive reactance. So you see the negative values on the vertical scale over here. And what it shows as a counterpart to what we have for Poisson ratios of 0.5 for fluids and water, oil. Well, for those acoustic mediums, the reactance stays positive. Okay, it's like it's having an inductive behavior with a series resonance, but it stays positive throughout the frequency or frequency band of interest. But as you move on to the solids, as the Poisson ratio is decreasing from 0.5 to, let's say, 0.2. 0.2 is the case like if you have glass at its backing, and if you consider that glass to be rigid or long enough, then the wavelength that of the sound that is being radiated spherically into that glass medium, well, then the reactance is negative, which is suggestive of the fact that you have a compliant backing. It's like a spring, it's like a mass spring system, and the spring is modeled by a capacitance. I mean, each spring has its own Hooke's constant, right? So that spring is much harder to move as compared to what you have at the front of the CMUTs. At the front of the CMUTs, you have a membrane which is more compliant. So at the back, the spring is less compliant. So it can be 1,000 times less compliant. So that gives you a very large capacitive reactance. So those values are negative for Poisson ratios less than, let's say, 1/3. That's what we're seeing. But these impedances, wave impedances into the solids, which have been derived by Blake, are for solids which are rigid and are long solids compared to the wavelengths. Okay, this is not the case for a finite substrate, which I'm going to talk about later on. So, but before that, there's some work has been produced by the CMUT research group in Bilken, and what they suggest is to have the substrate loss, whether it is rigid or have a finite substrate thickness. I mean, the substrate thickness can be comparable to the wavelength, or it is less than the wavelength. It could be subfractional wavelength, but we have to include that impedance parallel to the transduction force in the CMUT models. And this loss, you can say, RC loss is representative of backing loss is representative of the vibrations of the ultrasounds that are being emitted at the same frequency but at longer wavelengths in the backing materials. Okay, why they're longer wavelengths? Because the longitudinal speed of sound is, if you compare it to glass, the glass has a longitudinal speed of up to 600 meters per second as compared to 340 meters per second in air. So the longitudinal propagation is going to have a very large wavelength, right? The shear waves are half as much of that speed of longitudinal. So this loss is representative of the vibrations in the backing material. Okay. Now you see, okay, if you remember, the radiation reactance has two terms. I think I'm missing a J term over here, but this second term, you see it has a dependence that has inverse relationship with the frequency. Is the wave number you see. So it can be written as a if you expand this term, then this term can be seen as a compliance, or the capacitance that is representative of the spring constant. It's the inverse of the spring constant. It's just like inverse of the Hooke's constant. Okay, so it has an inverse relationship with frequency, so it's a capacitive reactance. So you see ZB is the series combination of the component, similar to the radiation impedance, similar to that of the fluid, same morphology, but then it includes the compliance capacitance. So this capacitance has to be included with the real and imaginary parts of those are the radiation and radiation. That's the radiation impedance of the waves in the backing. Okay, as a function of frequency, and to that you have to include, for solids, not for fluids, for solids, you have to include for Poisson ratios less than 0.5 a capacitance which represents the compliance of the backing. Okay, and you can see for longitudinal speed of sound, which are much greater than what you have in the front medium, solids have a larger speed of sound. So this compliance backing is the capacitance is much smaller than what you have, for example, the capacitance over here, which is the compliance of the front plate, which is easily moved by the pressure or by the applied static bias. Okay, so but the backing compliance is a harder spring on the other hand, so the speed of sound is much higher, and you have a very small capacitance. So that means the capacitance of the backing, the overall impedance at the backing is capacitive. Okay, it's going to be a very large capacitive reactance at the backing. Okay. Now comes the case of finite substrate thickness. So we have been talking of, for now, the substrates which are thick, which are thick enough to to be not moved by those waves which are being propagating into the solid medium. Now, if you consider the case of a substrate whose thickness is less than the wavelength in the substrate material, well, as an example, if, for example, let's say you have a 40 micron thick CMUT plate over here, which is bonded to a glass substrate. Okay, it's a solid which has a Poisson ratio of 0.2, so you can consider it as a glass, and that glass has a thickness of 0.5 mm. That means when this plate vibrates, that is when you apply electrical signal between the top membrane, top electrode, and the bottom electrode. The plate starts vibrating, okay? And this plate sees two different medias of different impedances. For example, in the front there is air, but at the point where the plate is bonded or clamped is where it starts radiating into the backing, because these vibrations are being counterbalanced by the rim over here, by the substrate. And because these vibrations are being counterbalanced, you will have maybe out of phase vibrations at the backing, right? Just as those vibrations will be in reaction to the vibrating plate that you have bonded to the substrate, right? Because the substrate is counterbalancing those vibrations. So, but since the impedance is different, the wavelengths in these two medias are different. So, for example, for a 40 micron thick CMUT plate and let's say a 10 micrometer etched gap or cavity height, this CMUT is going to radiate at 77 kilohertz resonance frequency for air, and this corresponds to the wavelength of 4.4 mm in the front medium, and that has a K of 2, which is very suitable design frequency if you have to design, let's say, linear phase arrays which can steer the beam in the half space from let's say minus pi by 2 to plus pi by 2. So, but what happens at the backing is that at the same frequency, the wavelength is like 16, 17 times more than what you have in the front. So it's like 72.7 mm in the backing, and that corresponds to K of 0.12, which implies a point source which is radiating into the glass, right? So it becomes like it is radiating at DC. It's the frequency is much lower, and the wavelength is much higher. The K is much lower. Wave number is lower because the wavelength is high. So because the longitudinal speed of glass is much higher than that of air, so you see the thickness of the substrate, 0.5 mm, is much smaller than the wavelength in the material. So we have a finite substrate thickness, and what we believe is that once the plate starts vibrating upon application of electrical signal, when it starts generating the ultrasound into the medium, those vibrations are counterbalanced at the rim, and at that point, and at these 2 points, this membrane material starts radiating into the packing. Okay, and the glass is also vibrating just to counterbalance those vibrations. Okay, this is just this is COMSOL simulation of the total surface acoustic pressures generated in both the glass medium and the air. So you have a 90-degree sector angle. This is a 2D symmetric axis, a 2D symmetric model for a CMUT. And above you see there is a matching layer which absorbs the waves, and in the radiation medium, which is air, you can see you have a series of pressure fluctuations. You have regions of relaxed pressures and compressed pressures, higher pressures, and you can see those with the so for example, this blue is relaxed pressure, then you have more pressure, and this series of compression and rarefaction is what is generating the ultrasound. And the wavelength is much less compared to what we have in the backing. Backing is a very small light. It's 0.5 mm, and there's not much of a fluctuation. It has thickness, but it is a finite. The substrate thickness is finite, which is very small compared to the wavelength that we have in the backing. At the backing, we have a different wavelength. Okay, so this is just a 3D view of what is going on. The CMUT is vibrating, and the membrane is vibrating, and it is generating the waves into the air medium, which is being absorbed by the matching layer. But on the rear side, you have you have a finite acoustic pressure. Yeah, that is representative of the wave of the sound in the backing, but the wavelength is very large compared to the thickness of the substrate. Okay, this is just for an illustrative purpose. What happens if instead of a 0.5 mm glass, we have a rigid backing or a long backing, which is long compared to the wavelength. So this is 100 mm glass, okay? And if you recall, we had about 72.7 mm of wavelength in the backing, and this is representative over here. You see, this scale is about, you can see this is about 5 centimeters, and this is about 10 centimeters. So we had about 7 centimeter of wavelength, and you can see there are two relaxed pressure regions if you have a 100 thick glass substrate. But this is just representative of the fact that you have a very long substrate, and that long substrate is comparable to the wavelength, and you can see the uh, uh, pressure fluctuations in the backing, which is not evident over here because you have a thin substrate, okay, which is just being moved by those waves. And but yet it has different acoustic impedance. The backing has a different acoustic impedance as compared to what you had in the front medium. Okay, now how are we going to model this? Well, it is suggested in the literature from CMUT Research Group in Bilkent that the backing also appears as a bilateral CMUT. So you don't have zero displacement in the solid at the backing. It's a finite substrate. It's a finite displacement. For XP2, for example, represents the displacement at the backing. XP1 is the usual displacement at the front, and you can see XP2 is smaller, which represents that the solid backing is harder to move, and you will have smaller displacements at the backing. But it acts like a bilateral CMUT, which is radiating into both the spaces, front and back. So in this case, we can consider that we have a thicker membrane compared to the CMUT front plate at the bottom surface, which is also radiating to the air. So, but this is not the case when you have when XP2 is 0, that means you have a rigid substrate. It's not moving, and then the Blake's work becomes very much effective in modeling the CMUTs through circuit model, and you can have over here the Blake's impedance. But what if the substrate thickness is finite? It is smaller than the wavelength, let's say. Well, then what happens is, even if you have a solid which has finite substrate thickness, its compliance decreases inversely with the membrane thickness. Okay, so for example, a 0.5 mm thick glass is going to have a very small backing compliance CB over here, and the ratio of CM1 to CB is going to be like 1000 or more than that, because it's a thicker spring and it cannot be moved in response to the waves that it's going to have in the backing. So CB compared to the front CMUT plate capacitance CM1 is very small. Okay, so implying much larger impedance of backing segment than that of the front segment, rigid backing is justified again, which means that you still have a very large capacitive reactance, or you have a very large backing impedance. So if you have very large backing impedance, then this front branch can be treated as like open circuit maybe, but that has to be explained with the impedance measurements and how it can the circuit impedance with the substrate impedance can fit those measurements. That's going to explain. So to fit the measured impedance of CMUT cells fabricated on the same glass thickness, the compliance at the backing requires is 1000 times smaller than the front plate, because the glass is less compliant. It's a harder spring compared to the silicon. Okay, silicon is much more flexible and have a smaller thickness, can easily be moved by the acoustic pressures, okay, or the acoustic loading. All right, now, so for a typical bonded wafer whose characteristics are different from that of substrate, we have two boundary conditions. One is that for static displacement, you don't have any. But for example, when you bond the silicon wafer with that glass, and this is the glass substrate. At the rear, we have a glass substrate, and then we have an etched cavity of a certain gap height. So over the etched cavity, you have a bonded silicon, okay, which is suspended because of the cavity is evacuated, and you have a more pressure on the above of the plate, and it's going to depress it, right, with a certain displacement. So you're going to have a non-zero XP1 over here, and once it is bonded to the glass substrate, you don't have a static displacement at the rims. It is fixed over here. Okay, so that's a boundary constraint that the static displacements at the rims over here and here are zero. But this does not mean that when the plate starts vibrating, when electric is applied, the AC particle velocity is zero. By particle velocity, I don't mean the atoms of the substrate are going to move. Well, they have their own crystallographic constraints, but what is going to move are the meshes or the finite volumes of the glass, which are going to counterbalance those vibrations, and counterbalancing those vibrations in the reaction, they're going to move, okay, because they're going to have dispersive pressure and shear waves. So the AC particle displacement and the velocity may not be zero in the lateral R direction, even if the boundary condition exactly holds. So what I'm saying is that static displacement, there is no displacement. There is no displacement at the rims, okay? But in the lateral direction, once you apply the electrical signal, the particle velocity or finite volumes of glass are not going to be zero. They're going to move in response to those vibrations of the membrane, okay, because they're supporting those vibrations. So the boundary condition at the rim is responsible for the propagation into the substrate wafer laterally. So if the CMUT plate is vibrating laterally, it is propagating waves outwards, and uh, that constitutes the radiation into the backing, into the isotropic materials. Okay, so the point where it happens is the point where the bonded silicon plate with the glass is fixed. Okay, it is fixed at the rim. So it's just like if you can think of this as a springboard. I mean, if someone jumps off it, right, off in the swimming pool, let's say, so it's a pad which is going to vibrate, then it is going to, this vibration are being going to be countered by, since it is attached to the rim, it is clamped to the rim. The clamp conditions are different over there, but still those vibrations are going to be counterbalanced by the backing, which has a different wave impedance, right? So over here, even the CMUT membrane has a different wave impedance in air, and the dispersive waves or the pressure waves which you're going to have in the substrate, they're going to experience different acoustic impedances uh, depending on the substrate density and the speed of sound. Okay. All right. So here is a brief uh, just to check though that boundary condition if the AC particle velocity is zero or not. The boundary condition is that the silicon plate over here is fixed. It is bonded to the borosilicate glass. So this is again a 2D symmetric axis, 2D symmetric model built in COMSOL, which has a borosilicate glass at the backing. It is 0.5 mm thickness. It is like 500 microns over here. You can see the scale. And this silicon plate is about 40 microns, as I've been telling before. And the cavity is they're not too deep; they are shallow. So that is about 10 microns over here. And then you have air loading for the front on the front of silicon. So that air loading is going to depress the silicon for the static analysis, but the silicon is held fixed at the rim, okay, where it is bonded to. So just to check when you apply the electrical signal between these two plates, the AC particle velocity, you can see if you calculate the average of the velocity or average velocity over here, then it's not zero. The AC particle velocity is not zero. So that is finite, and it's a very high Q peak, which shows there's not much, I don't know, loss. But what it shows primarily is that even if the static displacement is zero, the AC particle velocity is not zero. And that's the point where we start thinking of that, okay, if that is not zero, then the finite volumes of glass or the glass meshes are going to move, and that is going to constitute vibrations in the backing. Okay, so let's see. And this is what I've been talking about, the boundary condition for the static displacement. So at the rims, you don't see any displacement. There's more displacement towards the center, but the plate is held fixed at the clamp edges. So over here, you can see there's those at that edge. There's no static displacement, but as you move away from that clamp edge, from the rim towards the center of the plate, well, then you have more displacement. There's more surface displacement. Okay, it's more displaced. towards the center. So these red regions showing more displacement regions. Okay. All right. Now, if you go on and apply the, for example, if the silicon plate is grounded and you apply the AC excitation to the bottom electrode, which is gold or it's a stack of titanium and gold which is deposited at the bottom of the glass. And when it starts vibrating, then you can see in COMSOL, well, uh, it does predict the frequency around 75 kilohertz, which is correct, which is what we measure. But what we don't have in simulations is that we don't have that elevated baseline, first of all, which is representative of the vibrational damping. And we also have a lower measured Q. But in the simulation, we have a higher Q. Well, why is that? Because the pressure acoustics are not enabled, first of all, in the backing, and the dampings are not available. So I'm going to show you how, if you include the damping into the glass substrate, then you're going to have those baselines. So if you include the damping, then of course the Q is going to get lower, and this baseline of the measured, the simulated resistance is going to match with what is being measured, and that is going to be suggestive of the damping or the vibrational loss in the backing. Okay. So and the blue curve over here is the reactance. The difference in the measured and the simulated COMSOL reactance is about 8 picofarad, which I believe is owing to the CMUT channels or the wires. Those are parasitic capacitance difference, and which if include, then these dotted red curve or the simulated reactance become much closer to what is being measured. Okay. Here's another CMUT. Same story repeats about the same parasitic capacitance difference and of 8 picofarad, but in the measured and the simulated resistance, you have the same baseline difference, which is suggestive of the vibrational dampings. So if you do not include the dampings in COMSOL model, you don't get those baselines. Okay, and that impedance has to go into the circuit models to show that you have to include that loss in order to match what is being measured to explain what is going on. Okay, so the physical explanation is the damping of those vibrations in the glass. Okay, this is a little bit about how we have, since I'm showed the measurements, how we fabricated CMUTs. So the fabrication occurred based on the uh, anodic vapor bonding technology. So we have a glass substrate, which you can see has etched cavities. The etching was done using buffered oxide HF solutions, and the gap height of 10 micrometer were chemically etched. And then you have the patterning was done first by a chrome mask using photolithography process, and then you have deposition of metal. Then you do the lift off, and once the glass substrate is ready for bonding, you bond it to an SY wafer, which has a finite thickness of a handle layer that has to be removed by RI process. Okay, and then there is a stopping layer of buried oxide, which is removed by BOE. So what happened that time was we had about, I don't know, 700 microns thick handle, and I think that was removed from RI processes, and then the SF6 gas, it stops eating silicon when the buried oxide layer is reached, and that layer is removed chemically with buffered oxide etcher, BOE etching, buffered oxide etching, and then you're left with the device silicon thickness of, let's say, 40 microns, and you have a passivation film over here just to avoid any shortening of two electrodes. Okay, so here are some pictures. So we have a diced silicon wafer on a 100 glass wafer, which is the packing material, and you can see those connection pads. Just to expose those connection pads, we have to dice it, so that's why it is square. And in the other figure, you can see it from the rear side that you have the CMUT patterns. So those are the bottom electrodes, which are connected to the external connection pads, to which the wires are bonded later on with silver epoxies for impedance measurements. Yeah, this is on the rare side. You can see those um, CMUT circular radiators, which have about diameter of about 2.8 mm. So those are large scale features. Yeah, but okay. So this is before bonding. But after bonding, this looks like something like this. So you can see the silicon plate is bonded over the uh, CMUT features, which are in the glass, 10 micrometer deep in the glass. And you take the wire connections from the connection pad, and then you have the impedance analyzer to measure the impedance. So this is how it looks like. So on the right hand side, you have these wires, and you can take the measurements. So for example, the top silicon can be grounded, and the electrical signal can be applied to the bottom electrode through the connection pads, and then you can sweep the signal from, let's say, I mean, whatever is the frequency range of interest in which you have the resonance you want to see, and you can sweep the frequency from impedance analyzer, and you can see the changes, how the impedance is varying with frequency. Okay. Okay, you can see over here that you have some finite depressions, and you can see those regions. Okay. So what happens is this is the point where the RE etching has stopped, and you have a finite depressions in the CMUT cavities because of the pressure, because you have vacuum in the cavity and the air is depressing the very thin silicon. So if you run a stylus profilometer over here, like DECTEC, you will see that 10 micrometer, from 10 micrometer, about 7500 nanometers has been depressed by the ambient pressure, which shows that the plate is not collapsing on the substrate. It is still hanging because of the air pressure that we have outside of the vacuolated cavity. Okay, so it's an uncollapsed CMUTs. They are uncollapsed CMUTs by the design. All right, now for this cell in which silicon is hanging, but it is clamped at the glass posts because it is fixed, it is bonded, and that's how a single cell can be seen as a cross-sectional view of it. And then you have a bottom electrode which is connected to the external connection pads where you give the electrical signal. You have passivation. In this case, we have alumina passivation, not silicon dioxide, so that has to be changed. So alumina is the loss tangent of alumina is much better than silicon dioxide. It's like 1 in 10,000, so you don't have much of uh, dielectric loss due to the passivation film, and it's about 100 nanometers, which was grown by atomic layer deposition. The gap height is about 10 micrometers. The plate radius is about 1.4 mm, and the membrane thickness is about 40 micron. And this circuit model is representative of the distributed quantity of CMUTs, like plate compliance, transduction force. It includes the acoustic port is terminated into the radiation impedance, which gives the measure of amount of how much force that is coupled to the radiation medium. Okay, then there could be an AC source of incident incoming pressure. For example, if an ultrasound source is transmitting pressure, and in response to that, your plate is vibrating, so that is the dynamic pressure. Then you have static pressure because of the ambient force. LRM has the acoustic analogy of this inductance is the mass of the plate, so it stays fixed. The mass of the plate stays fixed. VR is the particle velocity on the surface of silicon, and depending on the particle velocity and the radiation impedance, you have a measure of how much power that is being coupled to the medium. Okay. CMUT is representing on the electrical side the capacitance of the CMUT cell. IC is the due to change of capacitance, you have a varying IC current, capacitive current. IV is the particle velocity current because of the changing particle velocity, and this is where you apply the electrical signal. And as application of by the application of applied electrical signal between the electrodes, you have a certain velocity profile which is going to determine how much force. So VR squared by into the radiation impedance is going to give you how much power, that ultrasound power that the CMUT cell is going to couple into the radiation medium. Okay, so this is the model, but this model does not include any loss except for the radiation impedance. And if you do not include any other loss like substrate impedance, well, what you have is once you simulate these dimensional parameters, which I mean, since the lump components are defined in terms of those these dimensional parameters, you can go and have a look um, at the literature how these lump components are defined in terms of those parameters. But what I'm trying to say is that you're going to have a finite, you're going to have resonance because the compliance of the plate and the mass of the plate are there going to react, and at a certain frequency the combination is short circuit, at which you're going to have maximum velocity current, and you're going to have a resonance peak. But if you're not going to include any other loss, it's going to be a very high Q peak because ZRR is again very low. It is representing the impedance of air, so it's going to be very high Q without any baseline. So this is how it looks like. So for those dimensions, you will see that at 77 kilohertz, you're going to have a very high Q peak, and you don't have any other loss except that of air. And the capacitive reactance is as usual. I mean, that's the curve that you have for the capacitive reactance and the capacitive reactance, as you can see, is more dominant because of the structure of the CMUT. It's a capacitor primarily. It's a non-linear capacitor having a non-linear relationship with the charge and the voltage, right? So predominantly they're capacitive always. But yes, you have a very high Q peak, which is representative of very low loss in the device. But that's not the case when you measure the impedance of CMUTs. When you measure the impedance of CMUTs, well, first of all, you have the raised baseline, which I was telling before, and that raised baseline has to do with the damping in the glass substrate, because you're also introducing vibrations into the backing, okay, which is being counterbalanced by the glass. So you have that glass backing impedance, you have to include that impedance, and then you have even lower Qs, which is very much suggestive of the loss in the transducer, which is not modeled over here. Okay, okay, this is not, yeah, this one. So there's no loss over here apart from radiation impedance. Okay, so you have over here two CMUTs, CMUT 1 and 2, and you see that it's not dependent on the bias. Well, whatever the bias is, you still have that baseline, okay? It's not dependent on so it means with a certain bias, when you apply, the electrical signal starts sweeping it from 50 kilohertz to 100 kilohertz, you have that negative sloped impedance, okay? And that is representative of substrate loss, okay? And on the right hand side, you have the measured capacitive reactance, okay? And that is as expected of CMUT. Okay, now this is how you fit. If you have the correct tracking impedance, you can include this into the circuit model with the transduction force, and then you start looking at those baselines. So this loss is representative of the vibrations at the backing, and why it's important. It's not just important just to fit those measurements, explain what is going on, but it is important if you, for example, if you have to assess the overall noise in the transducers, then this is another source of noise which has to be included. And of course, I mean, people, they do include substrate loss, they do include frictional losses, they have dielectric losses, fine. But the substrate loss is also another source of loss. Is not another source of loss, but it has to be properly modeled. That's what I'm trying to say, because it's going to affect the received performance of CMUTs as receivers, let's say. So the important thing is that it's you have to model it properly so that it can be explained in the model, and you can then go ahead and measure the received performance of CMUTs as receivers or even in transmitters. So the transmitting voltage response or the receive sensitivity of CMUT is going to be affected by all the losses that goes into your model. Okay. On the electrical side, you also see the parasitic capacitance, which is required to just move the simulated circuit reactance and make it closer to what you are measuring. Okay, so for example, this is the substrate impedance, and this is the RC shunt branch impedance that goes into the model, so that you have that elevated baseline and you can come closer to what is being measured. So the measured and the simulated Q's quality factors are very close, okay, which was not the case over here because we don't have any loss, substrate loss, and no parasitic capacitance. So again, you can see over here, you have about similar morphology of the shape of the substrate impedance with frequency, and if it goes into the with the parallel across the transaction force, well, yes, you have this kind of a baseline, and you start looking at you start getting closer to what you're measuring. Okay, so if I have to explain this with the COMSOL, well, the question is that fine, if you have this RC branch over here, well, how do you explain that? What is the physics? What does it represent? I mean, you can have fitting functions like this in parallel to the transaction force, and you could start getting baselines in the circuits. But what is the physics, the underlying physics that is explaining or justifying that inclusion of that shunt RC branch across the transaction force? Well, let me show you with FEMs that what happens is that if you turn on the acoustics in the backing and you have different dampings for pressure and shear waves, you start looking at those baselines. For example, you can see the surface acoustic pressure for this one is different and you have a different baseline. If you start increasing the dampings, you might start getting very closer to what is being measured and start killing the quality factor. You see there's a different acoustic pressure where it's relaxed regions. Okay, over here this is more compressive regions like over here. So I'll just maybe I should show you this from COMSOL itself, what goes on. And if you can see my screen, I think, yeah. So you have multiple physics over here. You have, for example, pressure domain, you have solids, and in the linear elastic material, if you right click on it, you can add dampings. And those dampings, they come into both the domains. So you have silicon that is bonded, and then you have glass at the backing and at the back, and you can see that I have different pressure wave and shear wave attenuation at reference frequencies of resonance, right? So this is different for glass as what you have for silicon. So if you add those dampings and you simulate the response, you will start looking at the baselines, okay, in the real part of the measured the simulated impedance, okay, and this baseline is representative of the damping, because if I turn off those dampings, you don't have those baseline. You're going to again have a very high Q peak without any baseline. So this baseline in the measured impedance is because of the vibration in the backing. So let me show you what happens if I just close this. Yeah. So I'm going to disable those backing and these damping losses in the backing. So then if I compute again the impedance, you can see that you're not going to have, it's almost flat. The baseline of the simulated or COMSOL, what COMSOL is suggesting over here is going to have a flat baseline and about correct frequency, yes, and but a very high Q, different Q. So it's very different to what we are measuring. Okay, what we are measuring is a CMUT, which has finite vibrational say dampings, having finite attenuation coefficients in the solid material. Okay, so in order to properly model this impedance has to go into the circuit, which is representative of the damping at the backing, and that is going to give you an idea of how much noise a single CMUT cell can have and how it can affect the performance of a CMUT cell. Okay, so that's about it. I think if you have listened to this, then you will have a feeling of wow, CMUTs which have been produced by such wafer bonding technologies have such kind of a trend, which is like has a dropping characteristic with frequency. Because you see, I mean, the way we are as the experience that we have with CMUTs, the radiation resistance has a rising characteristic with frequency, but when you measure this, it has a dropping characteristic with frequency, the real part, and that is representative of the vibrations in the backing. So you have to include those loss as the RC shunt branch if you are modeling that by the circuit across the transaction force. Okay. Okay, that's all. And thank you very much for for listening and for your time. Have a good day. Thank you.